Okay, so the goal for today is to, at long last, finish proving the representation theorem, that the general recursive functions are representable. Now that I've said that, I'm sure that I've jinxed myself and condemned myself to not being able to finish the proof. But hey, let's see what happens. So last time I had gotten up to the point where I needed to prove the lemma that if that the minimization of a representable function is representable, and that's in the special case where the minimization of the function exists. So if you remember, going back to the definition of general recursive functions, we had this final inductive clause, which said that if f is a function which admits a 0 in the first for some value in the first argument, then the minimization of that function is also in general recursive. So that's the assumption that we need to make on the representable function to begin with. And then we're going to take the minimization of that function and prove that that is representable. Now, I'm not going to get straight into that theorem because there are a few lemmas that we need to write down first. And these lemmas were the last things that I wrote down in last lecture. So let me just start off with the first of these. So in agreement with the notation that I have in the notes, this is lemma 4.0.5. And it states that for all positive integers, we can prove the following. That for all w, if w is less than the integer representation of n plus 1 inside the system Q, then this implies that w is equal to 0 or ... w is equal to underline n. So this is w is equal to 0 or w is equal to underline 1 or w is equal to ... up to w is equal to underline n. Okay, so a couple of quick comments. The first thing to mention is that this is not a part of our system. So that's not something that I can syntactically write down. The reason why I can is because I'm using that as shorthand. So just recall that w less than n plus 1, let me just write this. So z less than x means or denotes, or yeah, let's say denotes, represents, whatever you want to say, denotes there exists y such that z plus the successor of y is equal to x. Okay, so that's shorthand notation inside this piece of syntax that I've written down. And I'm going to be using that all the way throughout the lecture today. Trust me, it is much easier to carry this notation through than it is to try to work with this the entire way. Okay, so the goal is that, or not the goal, but the trajectory for presenting this that I've decided on is I'm going to give the gruesome details for this lemma, and then I'm going to be more suggestive and proof sketchy with the ones that come after this. But hopefully what you see is convincing that we are properly presenting out the proofs and writing out the complete proof trees. They're decorated all around the room at the moment. The room being three things: the Roblox world that we're in, also the physical room that I'm in, and also the skull that I'll live inside. Okay, so the way that we prove this is by induction on n. And so the first thing that we need to show for the base case is Q can prove for all w if w is less than or equal, sorry, not or equal to, if w is less than 1 underline, then this implies w is equal to 0. Okay, and this is surprisingly difficult to do. So now I need to move over to one of these slides that Daniel has very kindly presented or put into this world. Okay, so I'm over here. So how do I gesture towards these? Can I draw on these? Maybe I can draw on these.
Yeah, they're boards. You should be able to just click on them and draw.
Oh, I think Underpaid Extra doesn't have. Oh, that's weird. I can see it in my world, but I can't see it on my iPad. I don't know what's with that. But that's okay. That kind of means I can work with it. Okay, so as I just said, we're going to proceed by induction on n. So I'm slowly going to build up a proof tree here. That's what's happening. This whole thing compiles down to just one enormous proof tree, right? But it's easier to understand if we look at it in bits and pieces. So let's start. Let's start over here. So the only observation that I want to make about this is I'm starting with the assumption that it's not the case that x is equal to 0, right? And I'm also going to... Oh, geez, does this have a typo in it already? So this looks a little bit fishy. Just give me
with
one moment.
Base case where n equals 0, but on the left you're saying where n equals 1. Oh, no, that's still n equals 0. My bad.
Yeah, so...
The question is, isn't this hypothesis the thing you're trying to prove? Is that...
Yeah, that seems a little bit... Wait, hold up. Sorry, maybe it's okay. I just need to remind myself of what's happening here. So... Oh yeah, I want to arrive at a contradiction. So I want to conclude that x is equal to 0. So what I'm doing here is starting off by assuming that it's not the case that x is equal to 0 and hopefully arriving at a contradiction. Okay, I understand. There's no mistake here. So what's happening here is this is just one of the axioms that is inside the system Q, right? So one of the axioms is exactly this. For all x, if x is not equal to 0, then it is the successor of some number, right? So I'm allowed to put that down as an axiom, and then combining that with the assumption that it's not the case that x is equal to 0, I can derive that there exists a y such that the successor of y is equal to x. And the point is, I'm going to contradict the fact that... Well, what else do we know about x? We know that No. That makes perfect sense. Okay, so the point is... okay, sorry about this. Point is, over here, we're also assuming that x is less than the successor of 0, right? And so what I'm going to end up doing is arriving at a contradiction with this hypothesis, which means from that I'm going to be able to prove that x is equal to 0, right? But I'll be proving that x is equal to 0 under a proof that has inside it a hypothesis that x is less than the successor of 0. So then what I can do is I can discharge this hypothesis. So this will end up discharged later on, and it will tell me that if x is less than the successor of 0, then that implies x is equal to 0, and then that will have been done so with an arbitrary choice of x that satisfies the required property for all introduction, and the final line will be a for all introduction, and then I get for all w. If w is less than the successor of 0, then w is equal to 0. Okay, does that make sense as a general trajectory of a proof?
Yeah, makes sense to me.
Okay, good.
You said it would immediately contradict x not being equal to... Wait, x being equal to 0 if x is also less than the successor of... No. What was the contradiction? Right.
That's exactly it. So if x is not less than 0, but x is also less than the successor of 0, then after a lot of manipulation, you're just going to eventually arrive at a contradiction. And then that's a good thing, because then I can use contradiction... I don't know what it's called, contradiction elimination. It's the rule C bottom, and then I can discharge this hypothesis, and that will show me that x is equal to 0, and then I can discharge this hypothesis, and it'll tell me that x less than the successor of 0 implies that x is equal to 0. And then I've done that for an arbitrary x, and so I get for all w is less than the successor of 0 implies that w is equal to 0. Make sense?
Yeah.
Okay, good. All right, sorry about that. There was no error. I just had to reboot the proof inside my head. Okay, so the way that this is done is we first take this as a hypothesis, and then I'm allowed to use this as an axiom rule because it's one of the axioms inside the first order theory of arithmetic that we're considering. And then I just do for all elimination in order to be able to get an implication elimination to get this fact down here that that X is the successor of some element, right? Okay, and then what I want to get down to is the conclusion of this proof, which says that the successor of Y double prime plus the successor of W prime is equal to the successor of 0. And the goal will then be to remove the one of the successors on the left-hand side of this equality and the successor on the other side of the equality, and I'll end up with Y double prime plus the successor of something is equal to 0. And then I'm going to use the axiom that says 0 is not the successor of any element in order to get my contradiction. All right, so hopefully this first proof tree makes sense, and I'm using zeta in order to denote that. There's some extra baggage included in my notation. So what this extra notation is I'm carrying with me the hypotheses that proof is using, right? So this is just the proof tree zeta, which is on the previous slide, and I'm just reminding you that proof depended on the hypotheses. It's not the case that X is equal to 0 and X is less than the successor of 0. Okay. And with that proof, I ended up at this conclusion. So that line is exactly the final line of the previous proof tree. And now I want to use these two instances of existential elimination. The reason why there's all of this existential elimination, it's a bit annoying. It's just that I want to move the successor out of the brackets. So if we look for 1 second at the conclusion of this proof tree, then you can see all I've done is I've moved one of the successors out of the, I guess I've nested the successors, right? And there's an axiom that tells me I'm allowed to do that. It's the axiom that's right at the top of the board here. So for all X, for all Y, Y plus the successor of X is equal to the successor of Y plus X. But you can see that I can't use equals elimination until those two for alls are removed. So I need to remove those two universal quantifiers before I can actually use equals elimination. And it's the same for the existential ones. So I have this this statement with two existentials, and I have this statement with two for alls, but I can't use equals elimination on them immediately. I have to remove those quantifiers before I'm able to do that. I might pause to see if Billy has any comment on that, because I think he mentioned something about that last time I was talking. This is how I have to do equals elimination in the case that I have statements nested inside quantifiers, right?
Yeah, well, the rules of the system only work on the main connective of the formula. So yeah. So literally, this is not a very difficult thing that's happening here. I'm really just using this equals elimination. That's truly all that's happening. But I need to strip my statements of their quantifiers before I'm allowed to do that, and so that's why it ends up nasty like this. So my suggestion, as per last time, would be to write these trees down once in your life ever, and then accept them as derived rules, and then use them from that point onwards. You'll never get any steam if you don't do things like that. Okay, cool. And then once I have this conclusion, I then want to strip a successor from both sides of the equality, and then that will give me that Y double prime plus the successor of W prime is equal to 0, and from there I can get my contradiction. So now let's have a look at the bottom slide. The bottom side is doing exactly what I just said, and again, it's very similar. We have one of these axioms inside the system Q, which is that if the successor of X is equal to the successor of Y, that implies that X is equal to Y, and I can do that for all X and Y. The point there is that I can just subtract 1 for both sides, right? And I would love to just go ahead and use that, but before I do, I need to strip both my statements of their quantifiers. So I have these two existential eliminations that are getting rid of these two existential quantifiers,
and I have these two for all eliminations, and then removing these two universal quantifiers, and then once I have my statement that I'm after y double prime plus s of w prime is equal to 0, I can then introduce two more existential introductions in order to get this bottom line down here. So a huge amount of this.
That with the for all elimination, you're not literally just taking the quantifiers off. You're also making substitutions for like the for all statement is saying like for all x, but you're saying in particular I can choose like y double prime plus s plus the successor of w prime, and that's like that's what the
that's a good point.
Elimination is. It's not just in the way.
Yeah, that's completely correct. So I am indeed doing a substitution here. So you can see it's actually not that simple of a one because I've got the successor inside there as well. So yeah, there's a non-trivial choice in there. I'm substituting x for y double prime plus the successor of w prime, for instance, inside that step. And then I do another thing in the very next step where I substitute, it looks like y for 0. Okay, good observation. Thank you. And I'm not done yet. Once I'm here, I'm now set up in order to reach a contradiction, but I haven't actually done that yet. So I think I'm moving over to these boards over here. Okay, so this is the proof that I just wrote down on the previous slide, and I'm using it as this is my notation to say imagine the entire thing is sitting there. Now, the way it's written at the moment, you can see that I have these two hypotheses discharged. What that means is all the way back in my original proof zeta, the two hypotheses there existed as hypotheses, and then I've discharged them. So that's nested deep inside what I've denoted nu here. But for the sake of reading this proof, it will be easier if you ignore that for now. Ignore the discharging, and then for now focus on this part of the proof. So this is where I finally arrived at my contradiction. And when I have that, I can do what is this? What's this rule called? Contradiction elimination or something. I don't know what you'd call it.
Yeah, I forget. I don't know. Contradiction rule. There's probably some Latin for it.
Yeah, I'm sure there is. Let's just call it the contradiction rule. And that is the point where I've discharged the first hypotheses, right? And you can see that with the labeling. So there's a 1. It's quite small, but there's a 1 as a superscript to the label of that rule. And that's labeling for you this discharging. Okay, and then, so let me spell out the contradiction for you. So as I already mentioned, we have y double prime plus the successor of w prime is equal to 0. So now what I want to say is that there exists some z such that the successor of z is equal to 0. That's clearly true once I have this statement, but I need to derive it. And I'm actually doing a very similar thing to what I did in the previous proof tree. So I'm using this axiom, which tells me that I can nest the successor. So it just says that x plus the successor of y is equal to the successor of x plus y for all x and for all y. And so I can take the particular choices. So what am I doing here? I've taken x to be y double prime, and I'm taking y to be w prime, and then I can do equals elimination once I've done my two existential eliminations here and here. And then I arrive at what I was after, which is this, that there exists z such that the successor of z is equal to 0. Okay, and then once I have that, I can then perform existential elimination, and I have the successor of z equaling 0 as a hypothesis here. It's discharged because that's the way that the existential elimination rule works. It's not a true hypothesis. It's just saying, look what I can do if I have a witness of this statement. And then I'm just using the another one of the axioms that was given to me as part of the system Q. It's just that 0 is not the successor of any argument. Cool. So that's me spelling out the contradiction for you. And then the point is, at this stage, I've discharged the hypothesis saying it's not the case that x is equal to 0. And then I can do a implication introduction and discharge the other hypotheses. And then I get x is less than the successor of 0 implies that x is equal to 0. And then I just do 1 for all introduction, and I finally have a successful proof of what I was after. Okay, and that's the complete tree. Does anybody have any questions about that?
Can I just point something out with regards to like wanting to do derived rules instead of this? This is another instance where I think you like want to use more derived rules in spots, but because you've like wrapped things in quantifiers and then needed to unwrap them later. So for instance, I think you could have taken this part here as the premise here, and then with this universal elimination, just eliminated x into that term y double prime plus w prime. Well, the successor of that is equal to 0.
Oh yeah, I can see that.
So
yeah,
then
that makes sense.
Your conclusion here would be a contradiction. Yeah, that's just a pattern that I keep seeing, that the proofs get bigger because as soon as you get anywhere, you want to like wrap it in a bunch of quantifiers, but then you just have to unwrap them later in order to make use of what's inside it.
Yeah, that makes sense. That's because I wrote these proofs separately. So yeah, I think you would see that more clearly if you did put the entire thing together, which I kind of want to do for this world at some point. I don't know if I want to have this demonic proof tree floating in the sky or something, but that's a good observation. So that's obviously just me being suboptimal with the proofs that I'm writing. It doesn't affect the argument in any way. I'm just after the existence of a proof, and that's indeed what I have. But yes, there are, as Billy pointed out, there are redundancies inside the particular proof tree that I've selected. Okay, great. So that's the base case of this argument, right? The next slide down is telling you what the inductive step is. So I now need to prove that Q can prove for all w less than the underline of n plus 1 implies that w is equal to 0. Oh, there's a typo here. Okay, all of these conjunctions should be disjunctions, obviously, right? Because I'm saying that w is either equal to 0, or it's equal to 1, or it's equal to ... or it's equal to n. Okay, so sorry about, and then it appears here as well. Okay, sorry about that typo. Okay, and this is where I'm going to start being more relaxed on fully explicating the entirety of the proof trees. So I've written down these derived rules here, and these are exactly the derived rules that Billy just pointed out that I have a tendency to seem to want to use. I guess that's a fact that we're going to have to swallow. I wrote these before that conversation that occurred just 2 minutes ago. Okay, and this is also a valid technique. There's nothing wrong with doing this. It's just that there might be a slicker approach. But all I'm doing here is trying to put in the rules that I want to use when they're buried inside quantifiers. So the first one of these, if I remove the existential quantifier at the very start, then I have this rule for free because it's one of the axioms of Q. So all I'm saying here is that if I put the existential quantifier in the front, I still have it. I think that's what I prove in the slide beneath. Yeah, that looks like the slide that I proved beneath. So now if we look at the slide on the bottom, all I'm doing here is taking this as an assumption, and then I'm doing exactly the pedagogically unwise trick that I've been doing this entire time, unwrap my quantifier, and then perform the equals elimination on the unwrapped axiom. corresponding to this this statement with the existential quantifiers that I'm trying to prove, and then you're done, right? Nice and easy. And then I do have the proofs for the other two trees written out as well. They're on the other side of the room, it looks like. Yep, come this way. Okay, and I won't harp too long on these ones. Maybe we can have a look at the bottom one, but the bottom one is not very pretty. All that's going on here is the management of the variable substitutions that I'm making, right? So the point is, if I have, oh, this board works on my iPad. Okay, so note to the developers, there is some difference between this board and the other ones. Anyway, the existential quantifier in front of the term t, and then all I want to, what am I deriving here? So I'm saying, yeah, I'm saying that if u is equal to v, then I can perform that substitution inside these existential quantifiers. But something looks weird here. I don't know why I have the... I don't know where this existence of x has come from. Oh, here's the typo. Okay, let me clear the board and fix the typo. Wait, hold up. This is an invalid existential elimination. Or is it? What is this rule? Sorry, let me get my notes. Right. Okay. Let me remind us what we're trying to prove. So the derived rule that I'm trying to show is that if I have these two things, then I can prove there exists x, there exists y, such that t, and then this is a substitution u for v. So this just means the term t with all instances of u replaced with v. And there is a typo, but it's not a big one. It's just that. So I need there exists x inside there, and then it's perfectly valid. So the point is with this x, let me use a different color. So the point is with this existential elimination, I'm taking this as a hypothesis up here. So that's my witness. And then for this existential elimination, I'm taking this thing and putting it up here. So that is my witness. And then the point is I'm not allowed to use the same y inside the existential quantifier as inside the witness. And so that's why I have to put y substituted for y prime inside. And that's what I've been doing this entire time whenever I've come across existential eliminations. It's just that previously I've had explicit terms, so I've just written the substituted thing out in full, whereas here, t is an arbitrary term, so I don't have control over it, so I need to actually put this substitution in. Okay, and then you can derive this rule. So all this is saying is I want to be able to substitute... Oh yeah, I want to substitute v into my term t, but v might not be something that I have a hand on, a grip on. So it might just be that there exists a y that makes this equality hold true, and then for that particular y, I want to be able to substitute it into t, and that's what this rule allows me to be able to do. Okay.
There should be some like conditions about like the contents of t and the contents of v. If there's any co-occurrence of variables there, I think you might violate some existential elimination rule.
That sounds like it's probably true. So let me think
Like-
for a second.
For instance, if T has, if T contains,
Y, then I've captured Y inside here. Is that what you mean?
yeah, I was
Oh,
more
no.
thinking,
Yeah.
I think it's if V contains like X or something, because you're obligated to get rid of any, oh no, actually X prime. If V contains X prime, and you like get to the final, you get to the exists Y T, substituting U for V, then you've got an X prime at the very bottom of that, of the second premise to existential elimination, but you're obligated to get rid of that X prime.
Oh, I see. I think I see.
But
So
I'm sure your usage of this rule hasn't fallen into any traps.
yeah, this would be so is it just up to free variable capture? Is that sufficient? Because that's kind of the problem, right? You might have Y prime. No,
No, but X
you
prime
might
isn't
have
being
Y.
captured. X prime isn't necessarily being captured by any
Yeah, X prime's not being captured.
quantifier.
Well, then I'm not sure I see the problem. If I just replace X for X prime inside T. X is a variable, right? So there's no problem of like X prime containing an instance of U or anything like that. So it might be okay. So what's this? What do I need to say?
If you just
Okay, let's just look at it.
What if you just imagine V to be the variable X prime? I think it survives to the end, to that second premise of the bottom rule. As in, your existential elimination here is eliminating this variable X, and it becomes X prime. And then you do some reasoning, and that reasoning is supposed to get to some conclusion that doesn't involve the term or the eigenvariable X prime. And yeah, which is like, again, your conclusion here. But if V is the variable X, if V, the term V is just the variable X prime or something like that, then X prime survives all the way to here as long as there's a variable U in the term T. So then you have a term, a formula involving X prime that is supposedly following from the existence of X, but like you just sort of threw it in there.
Yeah, that makes sense. I have, yeah, okay, so that's correct. That's a problem. And the fix, right, is just that I have control over this X prime. So I can just pick it to be a variable that does not occur in T or U or V, and then there's no way that I can run into that issue. Right?
Yeah, okay.
Okay, cool. So let's just say, and then I need that for Y prime as well. Okay, so that's the condition that we need, and that can always be satisfied, so that's fine. Okay, good. And then the point is that you then kind of split the proof into two cases. So either W is equal to 0 or it's not equal to 0. And if it's not equal to 0, then W is equal to the successor of something. And so I can get successors all over my equations. Well, let me write this out. I'll go to the board to make it precise. But the point is, at this stage, I do have it here. Okay, cool. So if you look at the second board, so what's happening here is I'm starting with the assumption. So just keep in mind what I said about the shorthand notation for less than, right? So this really says for all W, W is, so I'm having a hard time writing without it being visible. Okay, that looks a little bit silly. That's fine. N plus 2 underline. All right, so what I'm saying here is that for all W, oh, why do I have that for all there? That's another typo. Sorry. Okay. There should not be a for all there. So this is just the hypothesis that, now I need to get rid of this one, that W is less than N plus 2 underline, right? And the point is that if it's the case that W is not equal to 0, then I'm able to derive that there exists some W prime such that W prime is less than N plus 1 underline, right? And then from there, I can appeal to my inductive hypothesis, and the inductive hypothesis tells me that in this circumstance, W prime is equal to 0, or it's equal to 1, or it's equal to ... or it's equal to N. And then what was W prime? Well, the successor of it is equal to W, right? So that means that W is equal to 1, or W is equal to 2, or ... or W is equal to N plus 1 underline. Okay? So the way that the proof works is W is either equal to 0, or it's either to the successor of something. And if it's equal to the successor of something, then I can strip the successors and then appeal to the inductive hypothesis. And then this proof falls through. Does that make sense? Are there any questions about that? I can write that on the board. So I'm going to the board that I've already written on, but I'm just going to clear it. Okay, so okay, and under the case that W is equal to 0, it's easy to prove that W is equal to 0, or it's equal to 1, or it's equal to ... or it's equal to underline N plus 1. So okay, and then in the second case,
Sorry, do you really mean that W is equal to 0, or are you talking about N?
I'm talking about X, actually. So that... Oh, no, I'm not talking about N. I'm talking about W. No, I am talking about W. Once that typo is fixed, I've gotten rid of the for all. Why would I be talking about N?
Sorry, the sort of whole argument is by induction on N, right?
Yeah. But I'm trying to prove the following by induction on N.
Right. But so we're in the inductive case for N, where N is some number greater than 0.
Yes.
Okay. And
I'm trying to derive this sequent, right?
yeah, okay.
So the point is, I'm going to start at W is less than N plus 1. So that's my hypothesis of the proof tree. And then using the fact that N is greater than 0, I can now consider two cases when W is equal to 0 or W is not equal to 0, right? And if W is equal to 0, then I just use disjunction introduction, and then I get a proof of this statement easily. And so that shows that. And then the other case to consider is when, so the other case, yeah, let me go back to the second case is when we can prove that W is not equal to 0. And here we get that Q can prove W is equal to the successor of W prime for some W prime. So I guess that's really exists. So there exists W prime such that W is equal to the successor of W prime. And then the point is, once I have that, I'm able to get the proof down to a point where I have shown that W prime is equal to 0 or ... or W prime is equal to N underline, right? So the point is, all I need to show is that W, so first what I do is I prove, I derive inside Q that W prime is less than N plus 1, right? And the point is, once I can derive this, then by the inductive hypothesis on N, I can prove inside Q that W prime is equal to 0 or ... or W prime is equal to underline N. And then from this, we obtain that Q can prove that the successor of W prime is equal to 1 underline or ... or the successor of W prime is equal to N plus 1 underline, right? And the successor of W prime is equal to W. That's what I've already shown up here. So we finally conclude that Q proves W is equal to 0 or ... or W is equal to N plus 1 underline. And then that's what we needed to show. So that shows the inductive step. That's a sketch, obviously, of the inductive step. Make sense?
Just to note, Will, that the camera didn't follow you to that board because you didn't move. So maybe if you want to move over there for a moment.
Yeah, that's a shame. Okay, I'll take this as a moment. Plug my iPad in. I wonder if it'll lose battery anyway. Okay, let's move over here. Okay, lemma 4.0.6 is the last thing that I need before I can just prove that the minimization of appropriate functions is representable. And I'm not going to prove this lemma. I'm just going to state it. So again, it's a relatively simple, just elementary fact about numbers that I'm just claiming is provable inside this system Q. So it's the trichotomy axiom. So the lemma states that Q can prove for all x is less than underline n, or x is equal to n, or n bar is less than x for all n an element of the natural numbers. Oh, maybe that's a bit confusing, so I'll say. Cool. So for all natural numbers, n greater than or equal to 0, Q can derive the trichotomy axiom. Okay, so now with these two lemmas, I can finally prove the final inductive clause of the statement that the general recursive functions are representable. So Now we want to return, and I'll write out the proper statement so that it's nice and clear what I'm talking about. Okay, so this is a claim. F from n to the power of m to n be representable. Represented by f x1 up to xn y, say. Okay, now the argument will actually use the fact that Q is consistent, which is a little bit interesting. It's a bit of slickness involved in this argument. So I'm going to say if Q is consistent, then the function mu f, assuming that it exists, so that's a condition on f there, is represented by the following formula. And again, this makes perfect sense what I'm about to write down. So fy x2 up to xm comma 0. So what that says is that, well, what it quote unquote says is that f evaluates under y to 0, well, with y in the first argument and x2 up to xm on the other in the other inputs. And we ask that for all w, if w is less than why is that x1? That should be, okay, it's another typo.
Sorry,
So
what
for
were
all
you
w,
saying? What were you saying that the first formula says? Where did 0 come from? It just says f, y, x2 up to xn.
yeah, keep in mind that this bottom argument, the final argument is what we think of as this is what the function evaluates to, right?
Sorry, it
So-
didn't show up on my screen, that final 0 for some reason, but I just had to
okay.
close back from the board.
Right. No worries. Okay, and then for all things less than x. Oh, no. This is x1. Okay, sorry. So going back here. So this is a formula with three variables, x1 up to xm and y, and this is the only appearance of x1, but it's important that it is x1, implies it's not the case that f of w x2 ... xm 0, right? So this is just our formula that is telling us that y is the minimum value for which f evaluates to 0. Makes sense. Okay, and I'll denote this. Gx1 down to xn y, and then what we need to show is if mu f n 2 up to n m is equal to k, then Q can prove for all y, gx1, oh wait, no. Oh, no, I have made a mistake. Okay, sorry. Okay, returning back here, this x1, that's just meant to be a y. And you can see that down here, because what I need to... Yeah, so this argument here doesn't exist. And what I'm saying is n2 underline up to nm underline k y is true if and only if y is equal to underline k. So let me explain. Going back to what this argument says, what we are saying is that the minimization is the function that takes this value and says it's equal to 0, and that's the first time. So for all w less than that y, we have that it's not the case that f of w, x2 up to xn, m, evaluates to 0. Okay, so sorry about that typo, but what is on the board currently is correct. Okay, and now I want to prove this, so I'll move to the other board. Okay, here's the proof. So first, let's assume that our function evaluates to a particular argument. So let n2 up to nm and k be such that mu f of n2 down to n m. Oh, go away, k. M is equal to k. Okay, so first I will show that q can prove if y is equal to the underline of k, then this implies g of n2 underline up to n m y, right? So keep in mind that ultimately what I need to show is this biconditional, but I'm going to show this implication first. Okay, so I'm going to reduce the problem. So I claim that it's sufficient. So it suffices to show that q proves g of n2 up to n m k underline. And I'll just say due to the following proof tree. So what I do is I say, if it's the case that y is equal to k underline, and I have my proof of g n2 up to n m up to k underline, then I can use equals elimination and obtain g of n2 underline up to n m underline up to m. And then the next step is to use an implication introduction, which means that I discharge something. I'm going to discharge this hypothesis. So I get that y is equal to k underline implies g n2 up to n m y with underlines on all of these. And then I use a for all introduction and get for all y is equal to k implies g of n2 up to nm up to y, right? And so that is this. And so all I used was the assumption this. And so therefore it's sufficient to prove that. Okay, and then if we remember what J was, it's the conjunction of two different formulas. So by conjunction introduction, it suffices to show that Q can prove f of k underline n2 underline up to nm underline 0, and Q can prove for all w if w is less than k underline, then this implies it's not the case that f of w n2 underline up to nm underline evaluates to 0. Okay, and one of these is very trivial. So this follows immediately from the fact that f, lowercase f, is represented by capital F. Right, so it's only the second one that we have to show. So I'll jump to the other board in order to do that. Okay, and this is where I'm going to appeal to the first lemma that I wrote down at the start of this lecture. So by lemma, so it was 4.0.5. Which tells me that if I can prove that W is less than K underline, that implies that W is equal to 0 or ... or W is equal to N K minus 1 underline. So it suffices by this lemma to prove that for all N less than K, we have that Q can prove it's not the case that f of N underline N2 up to Nm underline 0, right? So the point is, once I have this, then I know it's not the case that any of these things evaluate to 0, and that exhausts the supply. So the point is, we know that W is less than K, and so W is equal to 0, or it's equal to 1, or it's equal to ... and then we show that for all of those possibilities, it's not the case that this thing evaluates to 0, then that's sufficient in order to prove it for all variables W that are less than underline K. Okay, and so the way that I show this, I'm actually going to appeal to consistency of Q here. So I'm going to say that we arrive at a contradiction if this isn't the case. So, oh, hold up. No, I'm not going to contradict consistency, but I will arrive at a meta-theoretic contradiction. I'm not going to derive a contradiction inside a natural deduction proof tree. So this is a bit interesting, what happens here. Okay, since mu f of N2 up to Nm is equal to K, this means, I probably should do that. This means for all N less than K, there exists L sub N, which is strictly greater than 0, such that f of N2 up to Nm is equal to L sub N, right? So let's think about this. What I'm saying is the minimization of f applied to N2 up to Nm is equal to K, which means K is the least integer such that f of K, comma N2, comma ... comma Nm is equal to 0, right? And so what that means is that for all N less than K, f of N, comma N2, comma ... comma Nm is equal to some non-zero value, right? And that's what Ln is here. Okay, it's also the case that f is represented by capital F. So I combine that fact with this fact. So also f is represented by capital F, and so what this means is that Q is able to prove for all y, f of N underline N2 underline ... Nm underline y, if and only if y is equal to Ln underline, right? And then I can use it for all elimination, where I substitute y in for 0, and I'll get that Q can prove f N underline N2 ... Nm underline 0, if and only if it's the case that 0 is equal to Ln underline, right? And what this means is that if it were the case, so if what it means is that if it were the case that this, if it were the case that this held for some N less than K, then I would be able to show that 0 is equal to the underline of Ln for some N less than K, right? But Ln is some positive integer, and so therefore 0 equaling the underline of Ln is the statement 0 equals the successor of something, And then we've already seen how that arrives at the contradiction, right? Okay, so let's write that down. Oh, I was meant to say if Q can prove this. Okay, cool. And so that shows the first part of the argument. I need to plug my computer in, so maybe I'll just take questions whilst I'm doing that.
So the conclusion is that Q cannot prove the statement for this particular n.
Yes, yeah. And it's not just this particular one, it's for all of the n's that are less than k, right?
Yeah.
Which is what we had to show. All right, great. So we're nearly done, and now my iPad's on low battery. Do you have another converter? Thank you. All right. Are there any more questions? Okay, everything is plugged in. Okay, so I need to act quickly now though, because these things run out of power even when they're charging. Okay, so now it remains.
Have you got your iPad on the lowest graphics quality settings?
Oh yeah, you asked me that before. I'm not sure, so let me see.
If you have it, the battery demands should be pretty minor for doing this. So I'm guessing.
Can I do that now?
Yeah, so go. Yeah, so click on the Roblox menu in the top left, go into settings, and then you should see
graphics quality.
So just tap the minus thing all the way down.
Oh, that is all the way down. Oh,
okay.
Oh, maybe I did that when you told me the first time. I don't remember. So maybe it'll be okay. It's plugged in now, and it was on like maybe 35% or something when I started. So maybe that's okay. All right. So it remains to show that Q can prove for all y, g of n2 down to n m underline y implies y is equal to k underline, right? So that's just the other direction of the biconditional that I had to show. And I need a little bit more space.
I thought you were going to continue with this argument because you've shown that Q can't prove a bunch of things.
Yeah, and then by lemma 4.0.5. So what I'm saying here is I need to show that, so the full thing is for all w less than k underline, it's not the case that this can be proven but with a k underline replaced for n underline here, right? So what I haven't written on the board is I'm saying start off with that hypothesis, and then using lemma 4.0.5, I know that w is either equal to 0, or it's equal to 1, or it's equal to ... or it's equal to n, or it's equal to k minus 1 underline, right? And so now that I know that they're the possibilities for w, all I need to do is prove that for each one of those possibilities, it's not the case that f evaluates that value to 0, right?
You've proven that Q can't prove that it is the case, but that's not the same as Q can prove that it's not the case.
I've shown that if I assume f of... I have shown that Q disproves it, because the point is if I assume that, so coming down here, if I have as a hypothesis f of n n2 dot 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 and n0,
Mm.
then I'm able to derive that 0 is equal to ln underline, right? And then this statement is 0 is equal to the successor of something, right? And then again, what I haven't written here is that from that, you're able to arrive at a contradiction, right? You're able to contradict the fact that 0 is not the successor of any value. And so what I've said is that if Q is able to prove this, then I'm able to derive a contradiction. And so I can then use contradiction elimination, whatever we're calling it, and then I can infer the negation of this thing, right? So I've shown that Q can prove that it's not the case.
Right. I think there's. I understand the argument. I think the way that some of your terminology is off, because you say if Q can prove this, then it can prove this like conclusion. But that's not the same as like Q can prove that with this premise you can get to this conclusion. That's completely different.
I agree that they're different, but where did I misuse it? So all I'm using is the fact.
That part.
Right?
When you sort of, I can understand the proof tree you're constructing, which starts with this with like the F formula as a premise, and then you get down to some contradiction somewhere. But then the sentence after, where you say if Q can prove that, then Q can prove this. That's like you've jumped into a different world of implication from which you can't actually get to the conclusion you wanted to get to. Good, like, because you're jumping from the inside Q implication to the outside Q implication, and once you go outside, you can't just chuck it back in. Like when you start talking about like meta theoretic statements about what Q can prove, you can't like from that infer like an implication.
Yeah, of course, right. But I am proving a meta-theoretic thing. Like there is an interplay between meta-theoretic and just theoretic things here, because I'm proving that for all n's less than k, Q can disprove this thing, right? And I claim that once you have that statement for all n, then you can construct a proof tree that actually shows you the original thing that you're after, which is this, but without that implication head, right? So what I'm saying is that meta-theoretically, you can infer this once you've proven meta-theoretically this statement, which is the statement that Q, as a logic system, is able to derive this formula. And I think that's a completely correct usage of the terminology. Am I mistaken?
I just don't follow how you get from the last sentence to whatever that conclusion is. Because just like looking at the last section, you're saying if Q can prove this, then Q can prove this, which is a contradiction, right? So from that, you can conclude that, it's contradictory. So it's not the case that Q can prove that.
I'm trying to say that once you have this, you can then use this fact in order to combine the proofs that you have for these two statements to get a new proof tree, right, inside the system that Q, using the proofs, using the existence of a proof of this statement and the existence of a proof of this statement, I claim that there exists a proof of this statement.
Yeah, right. But that's under the hypothesis that Q can prove f of n up to n2 up to nm and 0.
Yeah, but there the hypothesis is one of the hypotheses of the proof tree. So that's a legitimate thing to do. I can just chuck that in as a hypothesis and then I come down to a contradiction.
Yeah, right. But you're not like but that's not when you say if Q can prove this.
But I'm saying if Q can prove this, and then I point to a biconditional statement written inside the language of the type theory. So that sentence makes sense, right? Like,
let me give a suggestion. Instead of this part, I think what you mean to say is that Q with the premise, that's a comma there.
Mhm.
Dot proves that.
Mm-hmm.
That's different to saying if Q can prove the premise, then that. And you can actually use this thing to like derive what you're talking about here.
Yeah, that makes sense. So I think the confusion's coming from here. So yeah, you're right. What I mean when I say this is Q is able to prove this where I've used this as one of the hypotheses inside that proof tree, right? So yes, I'm in this. That's a good idea of this notation. I haven't actually used that before. Okay, I'm 10 minutes past time. Can I finish off this argument? I'm nearly done.
Yeah, go ahead.
Okay, thanks. Okay, so what am I trying to do now? Okay, the final step is to prove that Q can prove Y implies Y is equal to K underline. Okay, and yeah, so I guess I want to use this notation that Billy just suggested. So what do I say? Q under the assumption of G N2 up to NM Y. Okay, if it's the case that Q with this hypothesis can entail that Y is less than K underline, or Y is greater. Okay, let's not do that. Or K underline is less than Y. So if this, then Q is inconsistent. Okay, and then that's a contradiction because we've assumed a meta-theoretic contradiction because we've assumed that Q is consistent, and so therefore okay, I'm going to run into a problem here. So therefore we can't prove this statement. So, no. I want to say because I want to infer from this that Q can prove under this hypothesis that Y is equal to the underline of K, but I don't get that from this statement. So I need to say, okay, yeah, I should be able to do this. So, oh, my pen's dead. Oh, this is so annoying. Can I draw with my finger? Yeah, okay.
At least it wasn't the last line of the proof of the incompleteness theorem.
Yeah, but now that you've said that,
crawl across the line, Will. Crawl. Come on.
I'm gonna wrap me up saying.
Thanks, I can try. Yeah, we can try that. Okay, so I've also been handed a second Apple Pencil. So let me see if I can connect that to my iPad. Yeah, pair. Yes, okay. Thank you.
It's not dramatic.
No, it's not dramatic at all. Now, I just need a spare iPad and a spare computer as well. Okay, so what I actually want to do, I don't want to do that at all. What I want to do is I want to say that Q can prove it's not the case that Y is less than K, and it's not the case that Y is less, that K is less than Y.
Do you need Q plus
All right.
the assumption of G?
Yes, I do. Right? Because I can, using the trichotomy axiom, I can always prove that it's either the case that Y is less than K underline, or Y is equal to K underline, or K underline is less than Y. And so if I can prove under this hypothesis that it's not the case that either of these two things, then Q... Oh, my iPad died. Okay, Billy, do you reckon you can write out what I'm going to say?
Yeah.
Please. Okay, thank you. So now I want to say that Q can entail G.
You're not going to believe
into
that
underline.
was at 0%.
Oh no, really? Oh, dude.
Wait. I mean, I'll give it like 5 seconds of juice. It's at 2%. All right, let's go.
How hard is it to put a screenshot in? Because I can just screenshot my notes and then maybe we can chuck it in and then I can look at it.
No, it's not going to work.
Is that difficult?
What's the...
It's
where are
impossible.
So now what I'll say is Q entails G of N2 underline, comma, dot, 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 comma, NM underline, comma, Y, implies that Y is equal to the underline of K. Okay, cool. And the way that I do that is
Is that straightforward from this, or is there like some sneaky, like...
Oh,
like,
it's just using the trichotomy axiom that I didn't prove, but I insisted was provable, right?
Yeah.
So by lemma 4.0.5, I know that under no hypothesis whatsoever, I can prove that Y is... Q can prove that Y is less than K underline, or Y is equal to K underline, or K underline is less than Y. Sorry, I'm just pausing. I think I've noticed an error in this proof. So maybe let's discuss what I've got. I think that what happens is I contradict the fact that Q can prove this. So I just end up with the fact that Q can't prove that, but it doesn't tell me that Q can disprove it. So let's see if that's true. The point that I want to make is, okay, could you please write down lowercase f of K, comma, N2, comma, dot, 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 comma, NM is equal to 0. Okay, then if it was the case that Q was Q and the hypothesis of G with all the extra stuff was able to prove that Y is less than K underline.
What was the internals of G?
It's just the same as what you've already written up there. So N2 underline up to NM underline Y. Yeah, if that can prove... Actually, let's do the easy case. If that can prove that K underline is less than Y, yep, then since we have G, which has inside it that for all... Yeah, so write this down, please. Q with G entails that for all w, w less than y implies it's not the case that capital F of w, n2 underline, ... and m underline.
Implies what?
So this part is, it's not the case. So negation F, capital F this time, of W, N2 underline, up to NM underline. Okay, so and then you need a 0 at the end there as well. So W, N2 underline, up to NM underline, 0. Cool. Okay, so now the point is that we know for all w is less than y implies it's not the case that f of blah, blah, blah evaluates to 0. And then we are also able to prove that k underline is less than y, right? And so therefore we can, so now you can say Q under the hypothesis G entails that it's not the case. So the negation F, K underline, N2 underline, up to NM underline, 0. Cool. Okay, and now we remember what G was, right? G said for all y, f of k, f of y, comma, n2, underline, comma, nm, underline, evaluates to 0, and other stuff. And the other stuff I've already used. That was in the line, the penultimate line on the board at the moment. But we can still use the first part of that statement. So therefore, it's immediately a contradiction. We're able to prove that Q, so you can write this down, Q under the assumption G of the same interior entails capital F of K underline, N2 underline, NM underline, 0. Yeah, and this is an insufficient proof. Okay, so there's an error in this proof, unfortunately. So you can see here that what I've contradicted is the consistency of Q, right? And so therefore, it's just the case that Q under the hypothesis of G is not able to prove this formula. But that doesn't mean that it is able to prove the negation of that formula, which is what I actually need, right?
So this is the premise that gets you to contradicting consistency.
Yeah. And all that means is that that's not provable, but that doesn't mean it's... Oh no, maybe that does work. No, surely not. So,
Wait, you had a hypothesis that it was consistent, right?
Yes.
I don't understand what that means about Q with the addition of G being consistent, but if you knew that combined system was consistent, then this contradicts the hypothesis in the meta-mathematical statement that Q is consistent. So
yeah, but then all that tells me is that Q and G can't prove that the underline of K is less than Y. What I need is that Q and the hypothesis G proves the negation of underline K is less than Y, right?
Oh, I see.
And they're different, yeah. But actually, I think it might work. So what about the fact that we know Q can prove the trichotomy axiom? Like, Q can prove the disjunction of three things. So if I know meta-mathematically that two of those aren't provable, doesn't that necessarily mean that the third one is provable?
If it's complete, then yes.
Why does that use completeness?
Well, like, without appealing to anything else, it would follow from completeness, but what else does it follow from?
Like, I know that Q can prove the disjunction of 3 formulas, right?
So, hang on. The reasoning is, wait, which board are we in from this one? No, we're on this board.
We are zooming up on a hard stop on the recording in 5 minutes.
Yeah, okay.
Just quickly say what I was going to say. We know something like Q. Q can prove A or B or C.
Yeah,
And we know that
Q can't prove
plus
A.
G does not prove A.
Mm-hmm.
And Q plus G does not prove B. And you want to know that it can prove C.
Yeah.
Yeah, I don't think you can get there. Simply, like, you could get there if you had Q plus G can prove not A, and Q plus G can prove not B. Then you could get that it can prove C.
But the argument that I want to use is something like Q can prove A disjunct B disjunct C, and the only way that Q is able to prove the disjunction of 3 things is like in 6 different ways. You know, it either proves all 3 of them, or
what you're appealing to is a false fact about, like, if maybe actually let me just explicate the principle. It's that if Q can prove the disjunction of 2 things, then Q can prove A, or it can prove B.
Yeah.
This is called like the disjunctive property, and I think if it's definitely true that, like, if A and B don't contain like free variables, then like it's very trivial that it proves one or the other. Not in a constructive in a intuitionistic setting, but in a classical setting, you do have the disjunctive property. But it's specifically the fact that free variables show up that, like for example, Q can prove y equals 0, or y is not equal to 0. But like, you can't extract from this that Q can prove one of those things. And that's like, if you could split that into those like cases of provability, and you eliminated some of those cases of provability, then obviously you have like the remaining one. But as it is packaged together, like, because this disjunction belongs to like the internals of the proof system. If you want to eliminate those other cases, you have to do so within the proof system. That's kind of a guiding principle that, or like an intuition about like what you can and can't do with proof systems. So that leads me to think that you can't do this kind of reasoning that we were trying to do here.
Yeah, that makes sense. This is still in a general setting, though. There might be a way to make it work in this proof. I'm obviously going to have to look at it and come back. But yes, this proof is insufficient as it currently is. I'm sorry about that.
And on that abject apology, let us conclude. Thanks a lot, Will.
Yeah, no worries.
Thanks, Will.
Yeah, that's good.
Yeah, that's right. All right, we'll continue again next week.
Okay, see you guys.